Good afternoon, everyone. Our first talk will be given by Professor Yukun Chen. Dr. Yukun Chen is a professor in Suzhou University of Science and Technology. She worked as a postdoc in the College of Computer Science and Technology at Zhejiang University from 2010 and 2013, and received her PhD degree in the Department of Science at Shanghai University in 2010. Her research interest includes the economics of information, algorithmic game theory, combinatorial optimization, and blockchain. And today, she will give a talk on incentive study on strategic behaviors to BitTorrent resource sharing systems. Let's welcome Professor Yukun Chen.
Thank you, Yao Shuai. Thank you the invitation. Hello everyone. I'm Yukun Chen from Suzhou University of Science and Technology. Today I will talk about the recent development for the incentive study on the strategic behaviors in resource sharing system. This is a joint work with Professor Xiao Tie and Professor Xiaotie and Professor Qi Qi and some students from Peking University and Shanghai Jiaotong University. Our research is about the resource sharing on the P2P network. So what is P2P network? In the network, peers communicate with each other directly through the connections, and the peers are co-equal nodes. All peers pool their resources in a decentralized system. These two pictures represent the two different kinds of the network. The left side, the picture on the left side is the server-based network. So we can see if any computers want to exchange the resources must through the central server. But the picture on the right side is the P2P network. So if there is a connection between any two computers, they can exchange the resource directly. In a P2P network, resources are shared among multiple connected peers. Each peer is both a supplier and a consumer of resources. There are different kinds of the protocol to allocate the resources in the networks. One of the most popular the BitTorrent protocol. There are also different kinds of resources shared in the network. For example, the bandwidth, processing profile, disk storage, and so on. The utility of each agent is defined as the total received resource from the neighbors, from the other peers. Because the P2P network is open and decentralized, the peers can join and leave the network freely. They are selfish and also have the incentive to gain more utility, maybe by some kind of the strategy. Formally, the resource sharing system can be modeled as an directed graph, GVE with weight profile W. In this graph, each vertex V represents a peer. The WV is the weight of an agent. It is the amount of divisible resource that agent V owns. Gamma V represents the neighborhood of agent V. For example, in this picture, in this graph, this node load to its neighbor U. So we are very interested in the whole of the whole allocation, which is denoted by the big X. It is the resource allocation, the total resource allocation in the system, in the resource sharing system. Naturally, resource sharing can be modeled as a pure exchange economy, which is a special kind of algorithm market. In this kind of market, the player B sells its own goods to its neighbors as a provider. And at the same time, the player B is also a buyer of goods from its neighbors as a consumer. We consider a kind of the utility like this. Given an allocation big X, the agent V, the player V, can get its utility, which is defined as the total, the resource from all of the neighbors, the total resource from all of the neighbors. For the resource sharing problem in the P2P networks, there is one of the most important things is how to allocate resource fairly and efficiently. In the previous, some researchers have done a lot of work about the resource sharing allocation protocol design. They mainly consider about the fairness and efficiency. Especially in 2007, Wu and Zhang proposed the proportional response dynamics. In this dynamics, at the initial time, each agent allocates its resource equally to its neighbors. And at the time t+1, the allocation is proportional the resource from the agent U in the previous time. So this is the proportional response dynamics, which this dynamics reflect the fairness. So it means that agents may prefer to send resources to peers that send resource back to them, which is a tit-for-tat exchange scheme. It can encourage fair trading. For this, the very simple but very important dynamics protocol, Wu and Zhang provide and prove the very important results that the proportional response dynamics converges, and it converges to a market equilibrium. So what is a market equilibrium? A market equilibrium is a very important notion for characterizing efficient allocations in exchange economics. A market equilibrium consists of two parts. The first part is the price of goods in the market, and the second part is the big X, the allocation of the goods in the market. A market equilibrium must satisfy the following three constraints. The first one is the market clearance. The second is the budget constraint. And the third one is individual optimality. It means each player is optimally heavy for its allocation at the current price. Formally, the solution big X allocation can maximize utility for each player subject to the budget constraint. Breaking, what's wrong? Can you hear me?
Yeah, I think now it's better. Previously, your audio is like a breaking.
So in the last, you can't hear me before?
We can hear you, but your voice is kind of breaking. But we can mostly follow what you are talking. I think now it's much better.
Okay, I continue my talk. It's okay?
Sure, please continue.
Okay. Now, just I introduced the definition of the market equilibrium. And I just said the market equilibrium must satisfy the following three constraints. And we leverage the limit of proportional response dynamics as the resource allocation mechanism to allocate resource. Here is an example of the market equilibrium allocation, which is actually the limit of proportional response dynamics. In this picture, there are four vertices. The agent V can get utility, send nothing to the agent U1 because U1 sent nothing to him. And U2 sent 4-unit resource to V, and U3 sent 5-unit resource to V. So the total utility of V is 9. And then the agent V sent back 4/3 units to U2 and 5/3 units to resource to U3. Yeah, it's the example of the this is an example of the proportional response dynamics allocation. So in this paper, Wu and Zhang solved the fairness and efficiency of the resource sharing problem on P2P network. Our results and our interest focus on the robustness of the proportional response mechanism. We proposed the resource sharing game. In the resource sharing system, if the market equilibrium is used as a mechanism to allocate the resources among all of players, then a player may or may not follow the market equilibrium mechanism at the execution level. So the peers have incentives to play strategies to manipulate the mechanism, which leads to the resource sharing game. So from the perspective of the mechanism design, we are very interested in the truthfulness of a mechanism. So what is the truthfulness? A mechanism is truthful if no player can benefit strictly from playing some strategies irrespective of what is done by other players. And for a mechanism design, the input include a different kind of information. Some may be public, some may be private information. So for the strategic peers, they can misreport their private information. In our resource sharing game, there are two kinds of private information. One is the gamma V, the neighborhood of agent V, and the other is the weight, the WV, the weight of agent V. So the peers, the agent can manipulate its can conduct different kinds of the strategy by misreport its private information. We may discuss the three kinds of the cheating methods. The first one is the edge deleting strategy. It means that an agent may remove some edges connected to itself. The second cheating method is the weight misreporting strategy. That means an agent may misreport its weight. And the last strategy is the severe attack strategy. It means that an agent may create a lot of fictitious identities to represent itself to participate in the resource sharing in the system. Yeah, for the first two kinds of the misreporting cheating methods, we have done a lot of this important results. In 2015, SHT 2015, we proved that the proportional response mechanism is truthful for the edge deleting strategy. From the example we can see in this picture, the utility of the agent V is 9 if it truthfully report its neighborhood. But if agent V cut one edge, cut this edge, and cut this edge, his utility cannot be improved. And then in InJCA 2016, we also proved that the proportional response mechanism is truthful for the weight misreporting strategy. For example, if the agent V misreport its weight from 3 to 1, then its utility is decreased, cannot get more utility. So from these examples, we can see the proportional response mechanism is truthful for these two kinds of the strategies. So next we studied the cyber attack. In a P2P system, cyber attack is a grave threat and subverts the security of network by creating a large number of identities, using them to gain a disproportionately large influence. From this picture, we can see the green node represents the a peer. Then it can create several fictitious nodes, fictitious identities to represent him, to participate in the network, to participate join the network to participate in the resource sharing. Yeah. An agent creates several fictitious nodes connected to its neighbors, with its resource assigned among them by the CPU attack strategy. For example, on this picture, the agent V splits itself into two nodes, V1 and V2, and assign its resource epsilon to V1 and 3 minus epsilon to V2. Then the total resource from the resulting new network, the total utility is nearly 11, which is more than 9. The original unity is 9. It is obvious that the utility of V is increased. So for the resource sharing game, we want to ask the question that, is it possible for a player to deviate from the allocation mechanism by strategic behavior to improve its utility? If the answer is no, cannot improve the utility by player strategy, then we can say the mechanism is truthful for such a behavior. But if the answer is yes, it means that the agent actually can improve its utility by playing this strategy. Then we continue to ask, can we characterize the extent to which a player's utility can be increased by such a strategic behavior? So now we shall introduce a new concept of incentive ratio, a kind of ratio. The incentive ratio is first introduced by Chen Ling and Professor Xiaotian into ESA 2011. The incentive ratio is the factor of the largest possible utility gain that a participant can achieve by behaving strategically over the original utility when it plays truthfully on a given mechanism. So this ratio is the zeta V is the ratio of agent V, the maximal utility by playing a strategy over the original utility if it plays truthfully. Then we choose the maximal one among all of the agents. We got the zeta. Zeta is called the incentive ratio of the mechanism. So somebody maybe asked us, why do we to study the incentive ratio? Because in the distributed environment, all agents only have limited knowledge due to the decentralization of the system. They must make an incredible effort to gather the full information of the game and do complicated computation as well to pursue the largest utility. A small incentive ratio provides a safety margin for the proportional response protocol, since no agents will pursue a small improvement in its utility, which cannot cover their incredible effort. So a smaller incentive ratio implies an agent has less incentive to influence the allocation result from the proportional response protocol through strategic consideration, which reflects the robustness of the protocol. We have done a lot of several works on the incentive ratio against the CPU attack strategy. Our work mainly about some special kind of the networks and on the general networks. In 2017, we proved that the incentive ratio of the proportional response band mechanism for CPU attack is lower bounded by 2 and upper bounded by 4 on rings. So we can see from this result, we can see that there is a gap between the lower bound and the upper bound. Then 2 years later, we proved the upper bound and proved that the upper bound is 3 on the rings. But there is still a gap between the lower bound and upper bound. And this year, we tied the bounds. We proved that the upper bound is the incentive ratio is exactly equal to 2 on rings. So we completely solved the problem on the special kind of the networks of the rings. And then we also discussed other networks, other results on different other kinds of the networks. For example, we proved that the incentive ratio is exactly equal to exactly square of 2 on clicks, and also proved that the incentive ratio is exactly equal to 2 on trees. So we also until now we also only conducted the research study on the special kind of the networks. And we want to know we also want to know what's the result about the incentive ratio on general networks. So this year, AMAS, we proved that the incentive ratio of proportional response mechanism for cyber attack is upper bounded by 3 on general networks, because we know the lower bound on ring is 2. So the ring is a special kind of general network. So we know the lower bound of the incentive ratio on general network is 2. So the upper bound is 3 and lower bound is 2. There's a gap between the 2 bounds. We want to continue to tie the bound. Then in this year, we tied the bound of incentive ratio on general networks and proved the incentive ratio, the upper bound of the incentive ratio is 2, is only 2, matching the lower bound on general networks. It means that we have the completely conducted this work on the incentive ratio. Yeah. There are to obtain the tight bound of incentive ratio on general networks. A lot of the techniques, very complicated techniques are applied in our work. It is very complicated, and because of the limit of the time, I skip the details. And go to the result. Our result, the series of work result is about the robustness of proportional response mechanisms. In 2015, we proved that the proportional response mechanism is truthful for the edge deleting strategy. And in EDGAR 2016, we proved this mechanism is truthful for the weight misreporting strategy. And this year, we proved the incentive ratio of the mechanism against the cyber attack exactly 2. So we have completely conducted the result. We proved the robustness of this kind of the mechanism. In the future, we pose the problems generalizing the resource sharing model as a generalizing goal for future work. In more detail, are there any other attacks deserved to be analyzed? What does the market equivalent look like when there is a preference? And what does the market look like then? What does the market look like when there is more than one type of goods? Because in our model, there is only one kind of goods to share, and the preference is equal. The different pairs for this kind of the goods are equal. Only no preference, the different preference for this kind of food, this kind of the good. So we proposed the problem in the future and want to solve this the difficult problem in the future. Thank you for your attention.
Thank you, Professor Yukun Chen. Is there any questions from the audience? Can I ask you a question? you mentioned about, thanks for the great talk. And you mentioned about that the proportional response mechanism has a incentive ratio exactly 2. I'm wondering if you look at other, is it meaningful to look at other mechanisms? Can we achieve like exact truthfulness for other mechanisms, or do you have any impossibility result on the exact truthful mechanisms?
Yeah, it's a question. It's a good question. That is, I think it's our future work, because in our work we only studied the proportional response mechanism, because the mechanism, the result of the mechanism is market allocation, market equivalent allocation. So we are very interested in this kind of the mechanism. Maybe there are other kind of the mechanism to allocate the resource in the system, but but the kind of different kind of the mechanism may not have the nice properties such as the efficiency, such as the fairness, may not have the nice properties. So if someone want to design a mechanism, have the advantages of fairness, efficiency, and robustness, I think it's a very maybe a difficult work to do. Yeah, it's also our future work to design a different kind of the mechanism. Yeah.
Yeah, thank you, Professor Yu Chen. Are there any other questions from the audience? Okay, if not, let's thanks Professor Yu Chen again for giving such a wonderful talk.
Thank you. Bye bye.